try sharing my screen. You should now see my screen.
Yes, but it's gone.
Like
okay,
this.
now it's better now. Yeah.
Yeah, sorry. Yeah, I'm using a tiling window manager, and then Zoom is always opening windows somewhere. Okay. Yeah, well, the technical problems everybody knows and has now. Okay, so we are online, and I would like to start the online session like I often do in the lectures. I don't have a complete view of all the participants, but I would like to invite you to answer this with the symbols that Zoom provides. So you have the check mark, something positive, something negative, and whatever. Here I chose a cup of coffee. So if you do using formal verification in research and teaching, or in neither, I don't really see the results. Okay, it makes it slightly strange. The symbols, okay. And I thought that was a normal Zoom symbols. Okay, but I think you get the point. So think about it. What you would answer if you have the symbols and in your Zoom. Maybe it has changed. And then think about this question now. Now imagine in industry, and what would be the answer here? So in industry, I have used the same methods as in teaching or research. I have used formal methods, but different methods, or I don't have used any formal methods. So how would the result be here? And now answering this in comparison to what we're teaching and then what you used in industry and what probably other people use in industry, that probably gives you the direction of the talk, what this talk will be about. So my talk is about online teaching. The online was dropped here because else the title would have been wrong. Online teaching, verification of C programs in applied computer science. And this is actually an experience report of a lecture that I did the first time last winter. It's a master level course, which is not compulsory, but many people do it because it's like theoretical topic and they have to do some ECTS points in this. The German name is Programmverifikation, so it's just program verification, and it's done at the University of Applied Sciences in Munich, where I'm professor in formal methods. And I will just explain a little bit all the things. So one is online teaching that I will explain, then verification of C programs and applied computer science. So what's special about universities of applied computer science, in particular in relation to program verification? Because this is not something that is usually done at the universities of applied science. Now, for the outline, I will give some background. I mean, many of you are from Germany, so they will probably know this. I will explain my choice of approaches for verification, the choice of language, which is C, which is probably not the very first choice for program verification in general, and the choice of verification tools. I will give two examples. One is Hoare logic deductive verification, and one is verification using floating points, so really C float values, which also gives you shows you that it's a very different things that can be verified or that were shown to be verifiable in this course. I will show a little bit of integration into online teaching, but I cannot give any differences between online and offline and in-person teaching, just because the only time I did this course was actually online. And I will give you some observations from the course, lessons learned, and some changes I do now, because now this winter I do this coursework actually again. Now, applied computer science is, the universities of applied computer science is a different type of university, which, as far as I know, in this form exists in Germany, Austria, and Switzerland, so in the German-speaking Central Europe. The difference is mainly that the focus is much more on teaching and a lot less on research. So we do have some PhD students, but a lot less than the universities have. Many students we have, they do dual studies. That means they actually have a contract with the company, and they work in the company during the term break. And outside the term break, they study. So they have a lot to do during the whole year. And the companies generally, they have a contract. They say, okay, they will give you some financing for this, and then in return, you work for the company. So this is the deal they have. The professors also, there's a special requirement, and the requirement is that every professor at this type of university has to have worked 5 years graduation, and at least 3 years of these 5 have to be outside of academia. And the goal is really that the students, when they graduate, they have learned skills that are more or less directly applicable in industry. So it should be really something they could be confronted with in industry. So this is the goal that we have. It's called employability, but I'm not sure that's really an English word, so I left it out. This is something we use in the German-speaking when we describe these universities. That poses some challenges for program verification. In general, most of our students, they have no, or at least not much background in logic. They have used logic a little bit in mathematics, some in others, but they might come, it's master level, so they might come from different bachelor degrees. The courses, obviously, they should have topics that are related to later work. But there should be a non-zero probability that they will actually be confronted with this in work. And they have no compulsory functional programming. So I use Haskell in teaching, but not in very much, in a lot of depth. So I cannot rely on the fact that people actually know functional programming. And there's also a difference. I mean, I myself, I have worked using functional programming, but I think most programming outside is still not done in functional programming. I would like to be like this, but it's still a niche where functional programming is used. So this influences the choice of languages that we can use for verification. And my own background, so I spent some years in academia, and I did work in formal verification in different areas. And also these areas where I did my work obviously also influenced my choice in verification approaches and in the languages that I chose for verification. So the choices that I made for the course, so there's no real book behind it, was stuff that I found and put together. I did an introduction to logic, in particular first order logic. I started with first order logic, predicate logic. I used a little bit of Lean, so not using Lean, but the tutorial of Lean, which is one of the puzzles, one of the murder mysteries I think I recognized from this. So this prepared really students to write down logic and read logic. Another choice I made was to stay with automatic tools. So I didn't really not want to use interactive theorem provers with tactics. I was okay, and this is what I used, having annotations in programs, but not using tactics or some kind of guiding the proof. It was just annotating a program and then running a tool, and either you get an automatically proved property or not. And if it doesn't work, then you have to strengthen the property or to correct the property. I thought that it would be too much work to introduce logic and theorem proving and using tactics. I wanted to present also different approaches to verification, not just one, simply because I thought that will increase the probability that someone might actually recognize this when they work in a later in a job. So I provided deductive verifications or hostile reasoning, which is probably the least likely that people will actually be confronted with, but it's nice to write down the properties really in this style. And writing a specification is probably something that people might be asked to do, or that might help them later, because I think really that writing down a specification is probably 80% of proving and 80% of formal methods. I did some abstract interpretation, because this is really an automated method that is fully automated, and it's widely used. There are tools that are used widely that do abstract interpretation, and software model checking, because this is something that I'm quite familiar with. So the other choices I made, so language and tools, I use C as the language for verification of programs, because it's probably the most well-known language that people might actually use in an area where verification is relevant. The other one might be probably Ada, but Ada is not actually that widely used, and probably people don't know it yet. C is something they know. I used the Framer C tool, which is a tool from the French organization CALIST. And this is kernel, which is called Framer C, and it's using, it can read C. It's quite powerful. It reads really a large set of all C programs, and it provides different plugins. And one plugin is this WP plugin. And this is a plugin that you can use for deductive verification. I used another plugin provided by Framer C, which is the extended value analysis, which is an extended version of abstract interpretation. I used, as a software model checking tool, I used CBMC, which is a C-bounded model checker, which was originally written by Daniel Kröning, which is, well, it's more than just a C model checker. It's the C prover framework. And now it's further developed at DiffBlue and probably also Amazon. And I also used Z3. So I really think that SMT solvers is something that, well, most students should know how to use, because it's something that is very usable. It's very accessible if you know how to use them. And it's probably even more likely that they can formulate some problem in SMT-lib using Z3 or some other solver than probably Pharmacy or CBMC in later work. And CBMC is effectively an SMT solver, and it's easy to show how C model checking is actually transformed into a SMT problem. And this is also what I do in teaching the course. There would have been a potential alternative. It is not limited to C. I think it would also be possible to do almost the same thing using Java, using JML annotations, maybe the Workhorse toolkit, which is developed at the University of Twente, and which would allow to use concurrency and to prove concurrent programs, which is interesting. So that might be a future work to use this for Java. And using JBMC instead of CBMC, that's just a front end which uses Java bytecode instead of C. Now let me show an exercise example in Hoare logic. So this is generally how I start. So I introduce predicate, first order logic, and then Hoare logic, the different rules that you can use. And then the tasks are given like this. So this is a program written in this kind of, well, generalized imperative language where everybody more or less has an idea of what it does. And I ask the students, okay, what will this program do? And then obviously it's quite obvious what it does. It sums up all the numbers from 0 to n, and then some will actually see, okay, yeah, well, you have this closed formula and you can write it down. So the task would here would be to find out what this program does and then prove it. So for this program, this was actually the first where I would do a proof iteratively during the lecture, showing this interactively, and really using all the annotations from Hoare logic, all the Hoare triples, and telling the students which rule would be used. But I would not write down for this program, I would stop writing down the proof tree. So for smaller programs, I would write down the proof tree. For this, actually, it would be very difficult to write down a full proof tree, at least in a text editor. But I would write down all the Hoare triples and also the invariants that you have to find for this while loop. And this is very often what is used in teaching using Hoare logic. And you can use this program and you can more or less directly translate it into C and use Pharmacy with the WP plugin to verify the correctness of all these annotations that are done here. And it would look roughly like this. So you see now it's a bit nicer colored. So everything is a comment. And if the comment starts with this @ symbol, it's actually a command for Pharmacy. It's called Axel, which is a specification language called, I think, Advanced C Specification Language. It's a ACSL. It allows me to state what actually sum means. So sum is here a logic program that says, okay, if n is less than 0, it's 0, and else it's n plus the sum and the recursive call. And this actually defines what sum does, and then I can use this to specify what is actually calculated here, because the mathematical sum is not necessarily defined. And then I write down the precondition of the program, which is that n is non-negative, and I write down the conclusion that in the end s, the variable s, holds the sum of all this. And the only difference to writing down the Hoare triples like before is that I have to write the invariant in a special syntax, which is here loop invariant in these two lines. It's not necessary for Pharmacy to have all these annotations, all the assertions that are written here, just to check that what I did manually is correct. And I can run Pharmacy on this. And what I would get is a warning, because in the new version, it will also ask me to say which global variables are assigned in the function. This is this here. And then I will see, okay, all 11 of the defined 11 goals are proven. And they are proven here with QED, which is an internal engine that simplifies logic. And 2 goals are actually verified using AltErgo, which is not a built-in, but a T solver, which is, I think, developed by the same group. And obviously, if something is wrong, then you will get less goals and you would have to look at the goals. But there's just information which goal did not work, and there's no information about what actually failed. And then another task was this, if you know FizzBuzz. So FizzBuzz is I think a hypothetical interview question to write a program that counts from 1 to 100 and prints fizz every time the number is divisible by 3, buzz every time the number is divisible by 5, and FizzBuzz if it's divisible by 3 and 5. And apparently this is difficult for some who apply for a job in computer science. But I said, okay, you write this program in C and prove it, but instead of printing, which is a side effect and not easy to verify, this is very different type of verification. They should use arrays, and at the point where they should write fizz, they get an array that corresponds to fizz. They set 1 and 0 for all the others, and the same for the other arrays. And this is non-trivial. C has a lot of small pitfalls that you can fall in and not be able to prove it. You can have overlapping arrays. Arrays might not be readable. All this kind of stuff can happen. It might also be difficult to, if you first clear all the arrays, or if you don't clear the arrays, it might be difficult to show that everything is 0 before. So there's a lot of things that actually can go wrong. So despite being simple, it's actually quite difficult. Then I come to the next example, which is floating point. So very simple program you have, it's called my apps. So it talks about the absolute value of a floating point value. If the value is negative, so this comparison does work, I return the negative value, else I return the value itself. And the task is formalize and analyze that the sign bit is not set. So this is the first type, the first kind of this question. And obviously this will fail. And this is the nice thing about using CBMC in this context. You get a counterexample, and it will actually show you the exact bits of the counterexample that failed. And in this case, people learn that floating point, IEEE floating point, actually has an explicit sign bit. And so we can have -0 and not just 0. And then second thing is, okay, formalize and analyze that the result is non-negative and compare it to 0.0. And obviously also this will fail. And people learn that there's actually not a number. And all this kind of stuff of floating point, peculiarities, edge cases are very nice, well, but not very easy, but you can have, in particular with C, you can have a lot of programs that will actually allow you to show a lot of these problems that you can have with floating point verification, which can be very hard. And also tools like Pharmacy do not really support. And to keep motivation a little bit higher, I also used this example, which is from id Software's Quake 3 and is now GPL'd. I think, well, most of the students, they don't really know Quake 3, but probably some who are retro fans know id Software. And this is a strange program, which has its own Wikipedia article, actually. And it's strange because it's clear what it does, because it's written down in the specification. It calculates the inverse of the square root of a number. It's used to normalize vectors. But the way it does is really, really strange. So it uses this constant, which is an integer constant, uses shifting here and the minus sign, and then it will actually convert the result into a float. And this is meant what's here, evil floating point bit level hacking. And I think this is a type of program that would be really hard to prove in another way. But with a tool like CBMC, you can actually try to find out what it does. And the students here were asked to find an interval for this input number, part of 0 to 100, the largest one they can find, where the relative approximation error is actually less than 0.1. And also finding out what larger intervals or smaller error bounds will actually do, which will increase the runtime of the analysis tool. Okay, I also had a small thing for solvers, so showing that you can, for example, for floating point, again, IEEE floating point, you can try to prove this lemma, which will actually teach them to see how a decision procedure, which can just say set or unset, can be used to prove a lemma for all inputs. And maybe I don't think you need it, but for some of these lemmas, it's also necessary to add another constraint. For example, saying that I don't want to have a not a number here, for example, because float could be not a number. Okay, so I'm done with the examples. Now for online teaching, what I did was probably the same thing that many of you did. I recorded videos and, well, allow the students to watch the videos before. Some did, others they do it well later in preparation of the test. That was fine. In the synchronous courses, I used a video conference system. Again, I used Big Blue Button, which is very good. All the data stays with us. I recorded everything. I did quizzes during courses, which is very good. This is really the, let's say, the lowest level of participation, but many people participate. That work very good. We used Moodle as LMS just to distribute video links, teaching material, and further information. We used Rocket Chat, which is just a chat system like we heard in the morning, for like Zulip or Mattermost or Slack or whatever. Again, it's a server that we have at the university, which makes it nice. It has a good integration with Moodle, but it's just the same as all the others. But for this kind of work where you have annotations that are just text, and they're also very short, all the programs, they fit normally, they will fit on one screen. So it's very good for exchanging here. So that was also the students said that they did not think it would work that good, but it worked very well to support students when they had questions. The exercises were distributed via GitHub Classroom. I stepped away from this. I'm now using GLabs, which is a tool developed by one of my colleagues, which is using GitLab. I can only recommend it. It has a little bit less features maybe, but it's using GitLab, and that's really nice because many people have a GitLab server, but GitLab is a proprietary system. But then again, for this course, a version control system was not really necessary. It was just for distributing everything and then collecting the code. People generally did not work in this commit style like they do for development. Now I also, I changed a bit what I do. I'm also additionally now having these quizzes again in a free to answer form using LiaScript, which was written by a former colleague from the University of Magdeburg. And this allows students to take the quiz also in preparation. And there's no bookkeeping, no data that is actually visible to me, so they can do it as often as they want. For this, so grading was interesting because there were, the grade were awarded for each task. There were eight tasks, eight papers that they had, 8 exercise sheets they had to complete, each 1 or 2 weeks. So a few 2 weeks, most 1 week. And each was practical work to do, so proving something, and then also writing an informal description so that I would see that people actually had worked on it. And well, nobody would observe them, so there's a chance of plagiarism. But what we have, so our the rules of the exercise, they say that we can have a short interview at the end of the semester. The interview is ungraded, so we cannot change the grade, but we can decide based on the interview that people did not do the exercises themselves. So that is, I don't know how, I did not find out that anybody did it not for themselves. So most people, they would actually be able to answer my questions. But this is a possibility that we have, and that made it possible that we could use the grading in this way. So for the observations, well, deductive verification can be very hard. C is very interesting and has many surprises for everybody, even then for me. Specifying what a program is supposed to do can be hard, in particular if you have real constraints. So if you have to add the constraints that all integers are bounded, then even the sum program is not easy to prove because you have to then take into account that you will not have an overflow. From a C, WP is really powerful, has some pitfalls in writing down, but that's fine. The extended value analysis. So I did not show any example of abstract interpretation because it didn't work too well, actually. It's good to explain, that's nice, but then using a tool, they are too powerful. They don't allow the students to look into the tool what's actually happening. So I'm still looking for a tool that allows me to do that. That's a quote you're probably aware of. Edmund Clark said it's impossible to overestimate the count example feature, and I can't just underline this. That's really great about model checking. And I need a little bit more difficult tasks. It was very good, the grades were very good, but also because, in some part, because the exercises were not too hard. So I have some nice effects if you have a C program with unspecified behavior, but we don't have that much time. So for further info and contact, the paper has a lot more details on the exercises that I selected, including also a little bit on the evaluation of the students. The material is currently not available, but I can make it available if you would like to have it. It's currently in German, but it would be, I think, easy to translate. I'm very interested in hearing about a tool for abstract interpretation for C, which is suitable for teaching. And I'm also looking for good possibilities to use form methods more in basic theoretical computer science, like formal languages and automata theory, like Lean4, for example. You can contact me if you have any questions with this email address. And if you're interested in pharmacy verification, there's a large document, Excel by example, by Jens Gerlach, who is at Fraunhofer Focus, who have done the formalization and verification of many different algorithms using C based on pharmacy, automated provers, and also Y3 and COG. Okay, thanks. I hope I did not take too much of your time.
Thank you, Matthias. It's great to see such a wide range of tools being used for a course that's kind of designed for practical applications and sort of applied sciences. So that was really interesting from my perspective. Were there any questions from the audience? Catherine, I think you've got one.
Yes, it's just a remark. I am surprised you don't also use the plugin EACSL, because it helps students to verify either their code or their contract by runtime verification. Did you try to use this plugin also?
No, I have not. I know about it, but I have not yet used it. But thanks for the point. I have to probably next time. I will have a look at it because it will probably help the students. I know there's another one that's actually using has a counterexample feature, but I think it's a proprietary one. But some kind of this where people can actually get feedback if something is not working would be really great. And so this is so the extended Excel plugin, right?
It is executable.
Executable, sorry, yeah. Okay, yeah.
And
that's a good thing. Thanks a lot.
I can insist on the fact that it really works. Student-wise, they are testing, but they are also verifying their contract, and it helps a lot.
Okay, yeah, thanks a lot.